going to be a little bit noisy for you tonight, Bill. No, that's fine. I guess we'll crack on. There will be others maybe join us, and we'll accommodate them as they arrive. So I'm assuming most of the people in the room are also going to be attending the exhibition and conference. So this is the device we're going to be talking about today. It's called a MIDAS meter, and we're going to give you a little bit of the backstory and, most importantly, how this can add value in your operations. So anybody that knows anything about valves understand that 75% of the emissions coming from sites are in and around your valve population. It could be flange joints, it could be bonnet gaskets, it could be seat to seal interfaces and relief valves going to vents and drains and flares. 75% of all emissions on site are coming from valves. That's a really important statistic. And it's important because we've started monitoring valves in a way that we didn't monitor them in the past. The maturity in the market is such that we've been monitoring other products, rotating equipment, which has this wear factor, where you expect to see late life failures for mechanical reasons. Valves have never really fallen into that category, but given that it's the main action on emissions, we should be talking about it. So what this device is going to do is going to be part of a suite of tools that you're going to use to find your valve problems. And this device here is focused on through seat leakage. So anything that's going to vents, drains, flares, all that good stuff, through seat leakage, things that are disrupting your process, this device is going to be able to find that leakage. So you'll see on the screen, it is now a multi-award winning product. And the reason we won those awards is contained in some of the stories that I'll tell in and around what we've been able to achieve with this device. But the key thing that pushed it over the line to get the Energy Industry Council Award is that it's now being used as an alternative to mandated tests by the EPA. So anyone who's doing pressure build-up tests on their larger valves, certainly on your critical valves, which are mandated for testing, you're going to see a major benefit by using this device because it's much faster, much easier. It's completely non-intrusive as a test methodology. And so we're not just talking about cost savings here, we're talking about efficiency, and we're talking about prioritization of repair scopes. So everything I've just said there is contained in the presentation. If there's any questions as we run through, please feel free to stop me at any time. I should give you a little bit of background on why I'm the person making this presentation. So I work with the Score Group of companies. I'm based in Scotland, but my job is international. So I've travelled pretty much every corner of the planet where there's oil and gas production or some associated downstream activities. After we've extracted the black gold, if you want to call it that, we are then in a position where we want to start doing some refining activities and other downstream stuff. So I've been in the oil and gas / valve industry for best part of 40 years, and I've been in the Score Group of companies for almost 30 years. I've been involved in valve diagnostics for more than 20 of those 30 years. So there's a lot of backstory here. There's a lot of experience I can share with you. I'm going to try and share most of that in the slides. But as I say, if there's something burning a question in your head, feel free to shout up. We can stop at any point and take a little detour. Importantly, I want to share as much knowledge with you as I can today. Any questions before we start? Everybody's in the right room? We're in the right place? Good. Sorry, I didn't catch your details as you came in there.
Yeah, absolutely. Okay.
Which company are you with?
With Inroad Resources, we're a service company.
Okay.
A lot of OGI, LDAR, that type of work.
Excellent. So some of those suite of tools that I've mentioned are already in your portfolio.
Yeah. Also, I used to be in the steam business, so I
Okay.
used in ultrasonics since the 90s. So very familiar with the technologies.
Excellent. So what we're going to what we're going to explain for you is the differential between ultrasonics and acoustic emissions, which is what we're working with here. So you'll see that'll be part of the presentation. Okay, before we start, I'm going to ask a question to the audience, and that is, what do you think is the primary function of a valve? Regulate flow. Okay. Any other answers? Open and close. Yep. Anything else? The primary function of a valve is to contain process fluid. If we can't contain process fluid, well, that's why we're all gathered here today. Emissions, fugitive emissions, through seat leakage leading to vents, flares, drains, etc. So fluid containment in the process is the primary function of any valve. It's why we always start when we manufacture new valves with a body test. We have to check the integrity of that pressure retention envelope. So what I'm going to show you here in this little video clip is an uncontrolled loss of containment, so that it focuses everyone's attention on why it's important that you check the integrity of your valves. So if I get this little clicker working properly. We've got a valve being pressurized. What we've managed to do is get to about 40 psi there. There's our good friend Dick the Dummy. So what you're seeing there is an uncontrolled loss of containment on a processed fluid. It's liquid, it's a relatively small volume, but you can see the stored energy is absolutely huge. That's about a 15 kilogram chunk of stainless steel getting ejected and hitting our good friend Dick the Dummy and bringing him to an unfortunate end. What we talk about is being in the line of force. You never want to be in the line of force. So when you're working in and around valves, understand that stored pressure and containment is the primary activity. Once we've got that under control, we can then start thinking about other things like through seat leakage. So hopefully that's focused everyone's attention on the dangers. When we operate valves in and around the process plant, there are pretty much three things that we want that valve to do in terms of process, because the other answers you gave me are all about managing the process flow. Okay, when you're talking about that, there's a safety element, there's an environmental element, and there's a process efficiency element. So when we operate normal process plants, we're exposed to high operating costs, high exposure to risk, and our efficiency suffers when we see those unplanned, unexpected failures in service. What we want to do by using condition monitoring tools is to move the needle away from the red bars and start focusing on the green bars. How can we take our operating costs to the lowest possible number? Because that helps us with profit margins. How can we minimize our exposure to risk and trend it to almost zero? I think absolute zero is a target. It might not be achievable, but we can certainly get very close. And then thirdly, we want to make sure that the process plant has maximum uptime. That requires reliability in our populations. So the key thing about all those elements is that when your valves start to fail in service, they give a really early warning signal, long before they cause that unplanned shutdown. So all of the tools that we should be using should be looking for that earliest possible indication so that we can catch it before it causes the unplanned reliability event. So that's how we move from red lines to green. The condition monitoring tools show us the early indication of where the problems are. We address them before they cause that unplanned shutdown. Everyone understands, I'm sure, that an unplanned shutdown is a far higher cost than a planned shutdown, because in a planned controlled environment, you can pre-order spares, you can do things in a shorter time period. The window of opportunity to effectively create a repair is much shorter. So everyone understands the biggest cost on the plant is downtime. That could be anything between $1 million or, as one of our customers told me a few weeks ago, $3 million per day. These are big numbers. The valve repair pales into insignificance when you compare and contrast those two numbers. So this technology should help us get to that 0 accidents, incidents, near misses. We should be helping our people stay safe on the plant on a daily basis. We should be protecting our environment from those fugitive and through-seat leakage emissions. When we minimise our operating costs, it seems obvious to everyone in the room that we're going to maximise our reliability and resulting operational profits. So there's nothing in those 5 boxes that we don't want to happen. We want all of that stuff to happen. So that means we need to deploy the right tools at the right time and do the right maintenance at the right time. When we do that, this will be all the outcomes that we can expect. So this is a really positive story. Condition monitoring will deliver all the benefits that are listed on the screen. When we take this into the environmental space, we have to think about how the market's changed recently. So I know that sometimes this gets a little bit political, and I'm not here to talk about anything to do with politics. I like mechanical equipment, and I like to understand failure modes. So putting the politics to one side, we go in cycles with politics, and it's often very polarizing. One minute you'll have someone in the White House that really buys into the environmental message. Next minute you might have somebody that, you know, is a naysayer when it comes to climate change. You know, as I say, I'm not here to talk about politics. Regardless of what part of that political cycle you're in, there's an advantage to using this technology and getting to the right space in terms of your environmental and social governance. So as we talk about this, as we roll forward, I visit process plants all around the world, and everyone's talking about ESG. If you want investment cash from any bank or any financial institution, the first question they're going to ask you now is, what is your ESG policy? What is your purpose? Where are you going with your business? Are you making a positive contribution here? So environmental social governance is really about, how do you protect your people? How do you run your business? Are you doing it responsibly? Is it sustainable? And are we protecting the environment? So all of that is now wrapped up into the KPIs, key performance indicators, that every CEO who looks after a process plant is now being judged against. So they're being impacted in a way that they were never impacted previously, and that is they don't get their bonus if their ESG policy doesn't deliver the outcomes that I just showed you on the last slide. So what that's been boiled down to in terms of measurable results, most organizations are now looking at quantifying scope 1, 2, and 3 emissions. So I'm going to clarify that a little bit later in some of the slides. But if you look in the second half of bullet points here, there's a whole rake of compliance standards and requirements that are now coming into play that just didn't exist previously. And so these CEOs are saying, what tools have we got in our toolkit that gets us to compliance on those issues? And if we don't have the tools and we can't meet compliance, we're not just talking about downtime and reliability anymore. What we're also talking about is potential fines. And if you've ever had the EPA knocking at your door, then you'll understand what those fines look like. They're really big numbers. And Steve and Scott and everybody that's involved in organising this conference fully understand what these numbers are. They're big numbers with lots of zeros. So we need to get in control of this, we need to manage it, and we need to demonstrate that we have it under control. So starting off with the right ESG policies, implementing the tooling, the technologies, moving away from LDAR. I caused a bit of controversy in the marketplace about 7 years ago when I made a presentation at the Valve World Conference, and I said, the title of the presentation was LDAR is dead. So there's a lot of people in the room got a vested interest in LDAR. They're really keen to know what I'm going to say. The reality is LDAR stopped short of where we needed to be because it had a missing Q. I'll come back to that later on. The Q is effectively what allows us to comply and make sure we're in control of our sustainability and our plant reliability at all times. Hi, come in. Can you have a seat? Make yourself comfortable. Which company are you with? This is MIDAS meter, valve leak detection, quantification and trending. In the right space? Good, excellent. Which company are you with? Marathon, brilliant. End user companies, we like that. So what we're talking about here is a leak detection tool. You've only missed the first couple of slides, so make yourself comfortable. We did delay because of registrations. I'm sure you'll be up to speed in no time. So in terms of where we're at in scope 1, 2 and 3 emissions, it's all about quantification. We need the tools to answer that queue that sits in the middle of leak detection and repair. So I'm trying really hard to get the hashtag LDQAR trending. It's not happened yet, but we live in hope. One thing's for sure, as I travel around all the process plants around the world, all CEOs, all maintenance teams, all health and safety teams, they're all having the same discussions. What are the top 10 initiatives that we see? So if we look down the bullet points here, we can see pretty much the top 10 that I am told on a daily basis. These are the initiatives that we're trying to implement at our process plant today. It's coming from the C-suite. CEO says we need to reduce our operating costs, we need to manage risk better, we need to be more efficient, we need more reliability in the plant. All these things are consistent. Everyone's chasing the same Valhalla, the same goals. So if you look at our product range, it's by no accident that all the green ticks are in the boxes under the blue columns. What we're talking about today is this handheld device, but we've got permanent installed versions of this, and we've got other products that lead on from this. So this is what I would call our entry-level product. If you want to start your journey on condition monitoring with valves, this is the tool you need. We will mention briefly at the end of the presentation some of these other pieces of kit, but you can see that we have designed and developed this tool to effectively address the top 10 concerns of our customers over time. And that's literally why we've won the awards, because 2 of these, we used them. We used very little of this other than to ask the right questions. Now that we've got the answers, we know exactly what to develop. So this is our rolling program. We don't ever stop developing our products. So you're going to see more benefits moving forward. We've published a whole heap of literature, which again, I've given most of you already my card. If you look at my LinkedIn page, these are all downloadable resources. You can also go to our website. We've got a YouTube channel. We provide these little guides. Normally we release them for the first time on LinkedIn, just to go on that knowledge share moment. These resonate really well. Typically we're getting up to 10,000 hits every time we introduce one of these little PDFs. So they are resonating well in the marketplace. Feel free to download them. That last one there, 11 important reasons to monitor the condition of your critical valves. It's simple, easy chunks of information to help you sell it within your own business. I mentioned just before a couple of you came in, we already have a happy customer in the room, which is always great news, especially when it's an end user. We'll come back to some of that survey work later on. But if we cannot demonstrate the advantages, why would you start using the equipment? That's the mindset that I come from. So we share all this information. If you come round by our stand in the expo, we've got a little QR code. I think we've got 15 case studies on a landing page on that QR code. So I'll encourage you to scan that. I do have the QR code with me today if you want it now. We can share that at the end of the presentation. But please download that information. These are not sales pitches. What we're telling you is what the equipment does. Because the first thing that someone that you're going to relay this story back on your plant to is going to say, well, what's in it for me? It's the favourite question. Why should I get involved? And these are all the reasons why. Okay. One of my presentations in the main conference is going to be on the additional benefits that are delivered when you start managing your emissions. This always starts with the emissions discussion, and it always ends with process efficiency, reduction of losses, efficiency gains, all the things that are on these little graphs our start position be in the top graph, our end position be in the bottom graph. I'm going to speak about these in great detail in another presentation, so I'm not going to delve too deep into it today, but if you are interested in that, come along to that session. I think it's on Thursday afternoon, just after lunch, and you can see all these little green highlights where the gains are made and how they are made. So in answering those questions, it's not just about the case study works, what was in it for someone else. You can start to think about what's in it for you specifically at your operating plant. As I said, this is not just about emissions. People have been talking for a while about the burden of additional work scopes, additional monitoring sessions. You know, that takes a resource. If you want to send a guy out in the plant to do this work, as we did it when I was refinery, it could be days worth of work, somebody manually taking all those readings. A lot more efficient to permanently install the sensors. That's layer 2 operation. So again, just think about that journey that you're likely to be on. If we can deliver value at step 1, you're likely to take step 2. So valve management. Just for the operators in the room, do you currently have a formalized valve management program in play? Hands up if you do. No? Valve management is a simple process. There's only 5 steps. People talk about total valve management. You know, we talk about intelligent valve management. Intelligent valve management with those 5 steps will take you to the best possible reliability. So this doesn't need to be a really complex system. Let's keep it simple. What most organizations do is they buy valves on the basis of someone a long time ago who was building a plant decided this valve should be in that slot. So the valve is defined on a valve data sheet. The valve data sheet goes to the procurement team. The procurement team go out to the marketplace and say, select 3 to 5 vendors who they think can offer that valve asset in accordance with the description on the valve data sheet. They put on their request for quote, RFQ, please give us your best price and delivery for the valve as described in the attached valve data sheet, along with your recommended 2-year operational spares. Why do operators do that? The answer is they want to manage the valve over its life cycle. They don't ever want to let the performance decay to a point where it causes reliability issues. So the concept is calendar-based maintenance, okay? Based on the manufacturer's recommendations. So the manufacturer loves this. He says, great, I'm going to sell you spares every 2 years. Spares are 3 times more profitable than selling the valve in the first place. So you spend a whole lot of money doing a whole lot of maintenance that maybe wasn't required. It's completely inefficient and completely ineffective at managing your valve population. Why do we keep doing that? It's learned behavior. So we want to break that chain, okay? I'm going to show you how to break a chain. So linear approach to valve management is what most customers do. The valve is supplied, it's run for a period, and then the OEM spares are fitted. Call it a 2-year cycle. Every process plant CEO or manager or owner in the world wants to increase the mean time between major turnarounds. Yeah, and does that resonate with anybody in the room? Everyone's trying to extend the mean time between major turnarounds. I hear it every day. Can we go from 2 years maybe to 3? Can we maybe push that envelope to 5? Some plants are talking about 8 to 10-year cycles on their major turnarounds. So the health and safety guys, the environmental guys are in a total tailspin panic saying, how can we let that 2-year operational cycle run 4 times and still be confident that that valve is going to do its work? The answer is you can't if you're not doing condition monitoring. So you take the safe option. When you buy that valve, you program in to your computerized maintenance management system, the thing that was supposed to solve everyone's problems. You're not going to forget to do the maintenance because it's already in the CMS. So you pull out the spares that you've had to store for 2 years. You then fit the spares. You've had downtime to fit the spares. You maybe didn't need to do that. So this is broken, because what happens is you keep going around that repair cycle every 2 years, having a major turnaround so you can take the valve out of line to fit new spares. It's broken. It's not efficient. Eventually, of course, all valves run to some failure point where you want to scrap it. And one element of that might be that you've got internal through-seat leakage, which has now caused erosion on the internal of the valve body because you've got impact jet of process fluid leaking. The first thing that comes into the leak path jet of whatever your process fluid is starts to get eroded by that impact of process fluid jet. That wears down the body thickness. Remember my first video, loss of containment is a disaster. So if you lose the ability to contain the process fluid in the pipe, you're in a dangerous position. So that is effectively one of the most common causes of run to failure. Erosion on the internal body wall, reducing its capability to withhold or contain the process fluid. So we'll scrap that valve and replace it with a new valve. Guess what? We go back into the 2-year cycle, even with a brand new valve. So this is broken. This is not efficient. We want to move away from reactive response. We don't want to go run to failure, because if you've ever been on a plant where failures happened, it's ugly. Yeah, I'm sure we've all seen the safety videos. So let's not go to reactive response. This is the highest possible risk that you could expose yourself to, and we don't want to be there. So how can we change that dial? How can we move forward and get better reliability and spend less money? You know, it confuses people when I talk to maintenance departments and CEOs when I say, do you know you can improve reliability by doing less maintenance? It fries their brain. They're just not worked it out. So that's what we're going to try and do. We're going to try and reduce the number of interventions. We need to quickly and easily understand where our problems are so that we can prioritize our outcomes. And our outcomes in some instances we'll be doing maintenance. In other instances, we'll be doing no maintenance, regardless of age of the valve asset. So here's where the science comes in from Nolan and Heap. Anyone who's been involved in reliability studies will know Nolan and Heap have come up with a number of different conclusions. The bathtub curve is mechanical products. Effectively, you have infant mortality, as they called it. You see some early in-service failures. We go through a pretty stable operating cycle, money. And then we see, in terms of late life failures, we're seeing that drilled down from mechanical failures in the field. Wear and tear, lots of different ways to describe it, but effectively mechanical failure. Now, the challenge is that every single operating company, until they fully understand what we're doing here, imagines that this is what happens to all their valve population. And you can imagine the life cycle for a valve pretty much starts off with an allowable leak rate at the start of life cycle, and at the end, that leak rate has grown too much, and you either want to remove it from service or repair it. So it seems kind of logical. But if you go back to all those reliability studies, what Nolan and Heap said, based on all their research work, was that that effectively covers 11 to 12% of your population in terms of failures. So all that effort that we're putting in to manage our valve population with calendar-based maintenance is effectively addressing 11% of the problem. So let me put that in perspective for you and tell that story in a different way. If you go to your bank manager and say, here's $1, and you come back in a year's time, how much money do you want back from your bank manager? You want at least $1 plus a bit of interest. In this equation, you give the bank manager $1 and it gives you 11 cents back. This is not good. And yet it's what we've based all our maintenance activities on. So we need to change that approach. Let's not focus on the 11%. The bad news for Nolan and Heap studiers is that the bathtub curve is just one of, as you can see on here, 6 curves. So what we're trying to do here is learn from the Nolan and Heap study and say, What is it that we need to do differently? There was two really important key pieces of information that flagged up to me in our early days on condition monitoring. Number one, time-based maintenance have almost no impact on reliability. Now think about that. That's what we do. As operating companies, that's what you do. That 2-year cycle of maintenance recommended by the manufacturer is having almost no impact on reliability. So why do we keep doing it? It's costing a lot of money to do that. The second thing is, every time you let one of your operators go out there and one of your maintenance team go out there and start playing with things, they break them. It wasn't broken to start with. How many times have we been in our own house, in our garage or a backyard, trying to fix something and we ended up making it worse because we weren't the specialists at that specific piece of equipment? So a very simple story that resonated with our nuclear market customers. And this is important for the emissions discussion. When you look at emissions from valves, one of the most common failure modes is the stem packing. And there'll be lots of conference presentations on stem packing materials, how to manage that stuff in box over its life cycle. So what we said in the nuclear conference was, if you send a guy out to walk the line and look at all the valves, he will find a valve or she will find a valve that has a stem leak. It's inevitable. And every maintenance person that walks around the plant has usually got a shifter, a wrench in their back pocket, and they go, that's easy, I know how to fix that. So what do? They tighten down the packing, quarter turn, half turn on the packing. If you're doing that on a control valve with an electric or a pneumatic actuator, and you put too much tension or friction into that stuffing box, you've now jammed that control valve in whatever position it was sitting in when you tightened the packing. So you've lost control of your process, and that could have a massive safety impact. So it might seem crazy that 40% of all failures on the plant are human induced, but the reality is those simple little actions that your maintenance teams are taking on a daily basis are contributing to that 40%. And it's hard to find because it's custom and practice. Everybody does it. Oh, it's easy. We know how to fix that. A couple of turns on the bolts. Fugitive emissions gone, but are you now about to blow up your plant because that control valve can't move? So really important part of the discussion. I'm a big fan of disruption theory. If we do what we've always done, we're always going to get the same results. So this is not about getting the same results. We want better results. We want better outcomes. So we need to do things differently. What are we going to do differently? We're going to introduce condition monitoring. Condition monitoring is what moves the dial from where you're currently at and all these problems I've described. And we're going to take you forward into that new space with lowest operating costs, minimum exposure to risk, and maximum reliability and profit, maximum efficiency. This is intelligent valve management. 5 key steps. I said it was really simple. Let's not overcomplicate things. Step 1, front-end engineering design. When the process is designed, some smart engineer guy will say, this is the valve you need to do that work, okay? That engineer will describe it in great detail, make it into a valve data sheet. He'll send that up to the purchasing team. The purchasing team then goes out to the marketplace. We buy the valve, and as SCORE, we also install valves. We can do all that work for you. At that stage, we want to introduce the new step number 3, which is condition monitoring. Go figure. We're not just a valve company, we do condition monitoring as well. We've worked out that step number 3 is the missing ingredient to get us towards this efficiency model that I keep describing. So condition monitoring will tell us the exact point, the optimum time on the valve's life cycle to make that maintenance intervention. We're not doing it based on the calendar, we're doing it based on the condition. So I'll come back to that point. We then move towards our maintenance activities. We're doing maintenance with cause. We're doing maintenance prioritized. So one of the things we did at Wynnewood, for example, was we looked at all the leak rates on all the valves. We exported the file from our little handheld computer device, into a CSV file, Excel spreadsheet. We went to the column that said calculated leak rate, and we said, sort this column top to bottom. Biggest number at the top, smallest number at the bottom. So you can take a slice there, the top 20% slice. In actual fact, in our experience, 10 to 15% of all the valves on site are causing more than 80% of the problems. So this concept of prioritization of your maintenance program comes from the condition monitoring data. You'll also see a green dot at step number 5. So we talk about intelligent valve management. The thing that makes it intelligent is not just the monitoring tools, it's also what we do with the information on failure modes. So why did that valve fail in the first place? If it's been installed for a few weeks and failed, there's a reason for that. If it's been installed for 10 years and it's not yet failed, there's a reason for that. So it's about understanding what are not just the impacts that you can measure, but what are the indicators that can be connected to those failure modes? Because we want to get ahead of the failure curve. We want to make our maintenance intervention before it causes unplanned shutdown activities. So learning from the failure modes allows us to look at the stripped down valve and say what went wrong. We can then feed that back to the engineering team. And here's the intelligent part, it's a closed loop. Closed loop valve management delivers efficiency because the engineer says we can make that recurring failure mode go away. We might change geometry, we might change materials, we might change operational capabilities, whatever. But learning from every single failure mode is what makes valve management intelligent. Every time we go around that loop, the expectancy of each individual valve in our process extends. So you're now thinking, if I've got to change those materials, do some engineering work, do some geometry changes, I've got two costs. One is management of change. Two is you need some consultancy on what to do next. Let me tell you, those costs are tiny in comparison with what you're going to get back in return in efficiency gains. So if it costs you an extra 5% to modify that valve and put in a valve that's going to have 3 to 5 times the life expectancy, guess what? If you took all your valves to 3 to 5 times life expectancy, you've just saved yourself, if you're on a 2-year cycle, 2 to 3 unplanned shutdowns or planned turnarounds. So big numbers. So we're all about reliability. We're all about making that improvement that takes you to that beautiful space that we've discussed earlier. We talk about RBI. So the guys who are in pumps and motors, rotating equipment monitoring have been doing this for a long time. Valves were forgotten. The land that time forgot. Yeah, we don't need to be in that space anymore. Let's use the available tools and work out what's the probability of failure, what's the consequences of failure, how often do we need to monitor that valve to be confident that it's still fulfilling its intended function. The minute it looks like it's not performing its intended function, we can start thinking about doing maintenance then. As long as it's performing its intended function, we're going to leave it alone. Of course, there does come a point on this cycle where we think the risk is so high that we don't want to rely on somebody going out and using a handheld device. We want to permanently install sensors. So we'll be somewhere on that continuum. Probability and consequences of failures allows us to select the correct monitoring tools and equipment to manage risk and prioritize our data set, to prioritize our maintenance activities. So it's all about efficiency. Infrequent manual surveys can be done with a handheld tool. If you want to move to semi-automation, then you need permanently installed sensors. I'm going to give you some bad news. Whilst we're all in this conference looking at emissions, there's kind of two areas where that's going to come from in terms of valves. It's going to be leaks to atmosphere or through-seat leakage is your primary things, or the flange joint that attaches the pipe end of the valve to the pipe end of the pipe. When you look at the most critical valves on your plant, you're not just looking at leakage as a failure mode. There are actually 48 recurring failure modes. That's bad news because you need more sensors. So what we've got in our continuous fully automated monitoring system is up to 12 sensors looking at your most critical valves, predicting in advance of failure those 48 failure modes. Now, it's not just SCORE that's working on this capability. I sit on the technical committee in ISA, TR 9605, and what they're looking at is all of those 48 failure modes and how they can be detected in advance of the failure happening. So if we can see that the trend towards a failure mode, we can do planned maintenance in advance of unplanned shutdown. So in terms of management of risk on your safety critical valves, you really want to go all the way past go, collect your £200 and be living at continuous, fully automated monitoring on those highly critical valves. It's a different system called VMAP. I'll touch on it today, but I won't really delve too much into it. People have been talking for a while now about data. Big data is going to answer the problems. Industry 4.0, anybody heard about that? You're sick of hearing about it, I'm absolutely certain. Big data for me is not the answer. And I'll tell you why it's not the answer. Because in Scotland, a few months ago, a guy came up to me after a presentation and said, yeah, we invested in big data. Our guys in USA, our head office, said, we have to invest in big data. So we started collecting all this data and we got to big data and we realized there was a problem. We wanted to create a data lake. What we ended up with was a data swamp. We had so much data and we didn't know how to analyze it. We didn't have the capability to do the analytics that would pull out the golden nuggets that would actually deliver some value back to us. So as we move through our technologies here, big data is the start point, bigger data is a midpoint, and the biggest data set is where the maximum value can be returned on your investment. The key to this is being able to do the analytics. How can we connect each part of that data set to a failure mode? That's where the magic happens. So this is all automated. You don't have to be an expert analyst to make that happen. We've done all the hard work in the background. We just deliver back to you where you can add value. So it's that little bit in the closed loop of 5 dots that says, what are we monitoring and what does it mean? And how's that going to drive our maintenance program? So it's all about improving reliability. We start with troubleshooting. This handheld device, entry-level product, sometimes customers just go out and say, I've got a problem in my process. I can see there's leakage, but I've got a manifold situation here. There's multiple valves. I don't know which one's causing the problem. If you're doing that on a flare line, and by the way, flare lines are the biggest emissions because flare lines typically have leaks on the valves that are difficult to find. So the flare's going on for days, weeks, maybe even months. You can't get to the root cause. This will take you to the root cause. But it means that someone has to go out and survey each of those valves manually, and you will find it. So that's troubleshooting, just where is the problem? So that's level 1 operation. Level 2 operation takes us to what I call value-based maintenance. Value-based maintenance is looking at all the data that we've been able to collect and say, okay, which are the valves that we really want to address in our next planned turnaround? Where can we make the efficiency gains? Step number 3, of course, is the Valhalla that I mentioned earlier on. That is trending and looking at rate of leakage change over time, because that's what takes us to predictive maintenance. So troubleshooting level 1, value-based maintenance level 2, and troubleshooting is peak performance. We want to take your process plant to peak performance. If we can get you there, we'll be the superstars that charged a few $1,000s to return on your investment many millions of dollars. So calendar-based maintenance, I've mentioned this already. Typically what happens in calendar-based maintenance is you have that recurring metronomic approach. The computerized maintenance management system said, do a planned shutdown every 2 years, fit OEM spares, and we'll be good to go for another 2 years. Nobody wants that anymore. They're saying, can the 2 be 3, 5, 8, 10, whatever? The answer to that question is yes, it can. At the moment, Your maintenance budget is being completely consumed by calendar-based maintenance, most probably. I can't say that for every operator because we are working with some who've already changed their approach. So how do we do it differently? Condition monitoring will be done on a risk-based inspection basis. And what you're going to find is when you start doing that survey work, most of the valves that you're repairing on that 2-year cycle are still okay. Now, you're erring on the side of caution by doing that 2-year maintenance intervention. It's just in case maintenance. But remember, 40% of all failures are human induced. Letting your guys play with those valves and, inverted commas, fix them might be making things worse. So you can see here in my new approach, we've had the same operating cycle over 10 years. Calendar-based maintenance says that valve got repaired 5 times. It wasn't actually repaired. You just fitted OEM parts. When you start introducing condition monitoring, if the monitoring equipment says the valve is okay and operating fine, guess what? Leave it alone. Don't touch it. Don't break what's not needing fixed, okay? So you can see in this example here, we did 1 repair over that 10-year operating cycle, and that already delivered 80% savings. Now think about what those 80% savings are. I'm not just talking about consumption of spares, right? I'm talking about downtime. Remember, downtime is the biggest cost. So if we can reduce downtime by doing less repairs, how many times have you been in that turnaround planning scenario? And someone says, we've got a limited budget and we've got a limited time frame. Which valves do we want to prioritize? How do you answer that question? It's guesswork most of the time, but if you're doing condition monitoring, it doesn't need to be guesswork anymore. You can do with cause maintenance. So, techniques and inspection tools. I mentioned already, this is entirely designed, developed, researched, manufactured by Score Group. Only available from us. It's the only thing on the market like it. It's one of many tools you will have been using on the plant already. And one of the challenges when I start talking about listening equipment, because we can use cameras to see things in more detail or different things. We can use sniffing technologies, gas analyzers to find gases, detect gases in different ways, more sensitive approach than human senses. When I start talking about listening devices, people say, yeah, we used that in the past and it didn't really work for us. And there's a specific reason for that. And the reason is the listening devices that were used in the past were listening in the wrong sound frequency response range. So what they did was they listened between 0 and 60 kilohertz. Human hearing takes you to 20. So by using ultrasonic equipment, it was effectively giving you 3 times human hearing capability. And the reason 60 kilohertz was chosen is because that's where the roots of rotating equipment monitoring systems are firmly embedded. So if you're using ultrasonic equipment for pumps, motors, vibration, you're typically listening 0 to 60 kilohertz, mechanical noise. When you dive into valves, based on our research, we know that you're not going to find the leaks with that equipment because the sound frequencies that we're listening for are happening at a much higher frequency. So that inconclusive result you got with those old headsets. The other problem with the old headsets, of course, is you go out in the plant and you start hearing all the plant noise. That all gets amplified. It's nigh on impossible to find through-seat leakage using that device. We've done it. We've tried. So our research centered on what is the frequency response we need to know. And we came up with the answer on acoustic emission sensors listening at much higher frequencies. So there's typically 3 frequencies above 100 kilohertz where a leaking valve is going to make a footprint. And that's what we've focused on. That's what we've tuned our sensor to do, is listen from a sensor capability range from 60 through to 600 kilohertz. And there's 3 peaks that give us access to an algorithm which we've designed to tell you not just the valve is leaking, but we've also correlated that back to a leak rate. So we can tell you how big the leak is. Remember I said LDAR is dead because it misses the Q, and we want to put that Q in the middle there. This is what it's all about. Correlation to work out where we are on the life cycle curve requires us to know leak rate quantification. So this device does that. Through seat leakage, we'll find it, we'll quantify it, and then we'll see how it's changing over time. This handheld device will do all three activities. Did you have a question? Quantification. Leak detection, quantification, and repair only when necessary. So let's all try and get the hashtag trending. Maybe we'll finally manage to do it this week. So like all products, we deliver this in a carry case, flight case. The key element of the toolkit is the listening device itself. So there's no headset, it just comes. The first question we're always asked is, will it still work in a noisy area? And the reason people ask that is because human hearing, 0 to 20 kilohertz, used to be 1/3 of the range of the ultrasonic device capability. So what we said was, we don't want distracted by plant noise. So we've filtered all that away. We've taken it out of our equation. That's why we tuned our sensor to only listen between 60 and 600 kilohertz. So that noisy area of the plant that you want to use this on is not an issue for us, because if you can hear it, it's below 20 kilohertz, and we're only listening starting at 60 kilohertz and going all the way through to 600. So even the noisiest area of the plant, this will give you the correct answer. No more guesswork, no more confusion. The other thing we're asked is, do we need a baseline from the brand new valve to make this device work in terms of quantifying the leak? The answer to that question is no. You can deploy this tool at any point in the valve's life cycle and still get the right answer. The reason for that is we've done all the research. The research on all the differential pressures, all the fluid types, all the valve sizes, all the orifice sizes, in other words, the leak path sizes, leak path geometries. We've done all that research work. One customer asked us, can we use this in the nuclear industry for a specific valve size at a specific pressure rating on a specific process fluid? And we said, yes, we can do that. And he said, I want my own algorithm to make that as tight as possible. So in designing that algorithm for him, we had 1.6 billion data points. So this is not easy research. This is not something you pick up and decide, you know, we're going to redesign a product, we're going to develop it next week. This has taken us 20 years to get a one-size-fits-all tool that you do not need a baseline from the valve on when it's brand new. So it's been a long journey for us. Exciting, we can now use it in any part of the valve life cycle. So deploying it in the field, we take readings from the valve body, upstream and downstream of the valve. We click this little switch on the front here. That sends a signal by Bluetooth into our handheld calculator device, which then converts decibels of noise into leak rate going through the valve. So we want certainty in our survey. If there's anything in and around our valve causing nuisance noise, we're going to be able to find that, and we're going to be able to eliminate it from our survey results. That is why we take readings upstream and downstream of the valve, as well as on the valve body. So this is a complete survey using technology. We start on the upstream side. We start with a background reading, make sure the sensor's working, and then we start taking readings from the pipework. Position 1 is upstream far, position 2 is upstream near. Depending on the valve size, we'll take at least one reading from the valve body. If it's a bigger valve, we'll take multiple readings all the way around the valve body. All the intelligence for how many readings do you take on which valve type, which valve size, is all pre-programmed in here. So literally, I can make you a leak detection expert in 30 seconds using this technology. So when you come up to the expo hall, you'll see we've got a little demo panel, and you'll be able to play with this. So I encourage you to come across and actually get hands-on with it. 30 seconds worth of intervention will let you find the valve leak. Yes.
So what would be the threshold on it, or it would just tell you, period, if anything's coming out from any part of it?
So there's a number of thresholds that we need to think about. There's potential banana skins in all surveys. The first banana skin I'm going to talk to you about is external noise. So any interference noise that's in and around the target valve that you're trying to survey. So this survey here, if this was our result, when you switch the device on, it'll say 21 plus or minus 1 decibel on the LCD screen there. That's effectively the sensor here in the onboard electronics. It will never change unless you've broken the sensor. So threshold of detection, typically for a conclusive leak detection, we're looking for at least 1 more decibel than what we've got as our background reading. So let's say we're in 21 plus or minus 1. Let's say we're at 23 decibels, and upstream and downstream of that valve we're measuring 21. We're talking about leakage there. So the more decibels of differential you get from upstream and downstream, the more conclusive your result's going to be. So again, these factors are all controlled by differential pressures, valve sizes, fluid types, leak path geometries. So lots of variables in that equation. So there are multiple thresholds that we need to get you to fully understand. But if this is our survey result, let's say we got, and every process has noise as well, I should point that out. So this could be actually 30 decibels at each of those positions, but we've got a flat line. It's exactly the same reading upstream on the valve and downstream. That valve is not leaking. I'm conclusive in my result here. No leak detected. In a leaking valve, we're going to see the peak signal on the valve body. So again, just for the purposes of translation, sometimes this gets lost in translation. When we say valve passing, we mean process fluid is passing across the seat-to-seal interface. It's not passing the test, it's failing the test, but fluid is passing where it shouldn't be passing. So peak signal on the valve body, we're seeing increase in decibels as we approach the valve, and as we move away from the valve, we see those decibels dissipate. High frequency sound signals do not travel over long distances. So we talk about signal attenuation. So that high frequency signal, even within a few centimeters, you're starting to lose that signal. So the further away you get, the more conclusive result you're going to see. We talk about near and far positions, and people get really excited about how near is near and how far is far. We cover all that on the training course. It's not a critical distance. What we're looking for is differential signal. Okay. So here is the science I've mentioned before. The threshold of detection for ultrasonic devices is on the left-hand side of the graph here. Threshold of detection that we're interested in is on the right-hand side of the graph. The dotted line, the vertical dotted line, is effectively 60 kilohertz. Ultrasonic equipment cannot find early leaks in valves, and that is where the biggest possible advantage can be delivered with condition monitoring of valves. So that's why we tuned our device to listen above their threshold of detection, typically above 100, above 300, and almost, well, just short of 600 kilohertz. Early leak detection gives you that advantage in your maintenance program. You can now start trending that leak over time. The reason people thought ultrasonic equipment was going to be the answer is when the leak gets really big, the ultrasonic equipment will be able to detect it. But you're already at a stage where you've got significant mechanical damage inside that valve. If you're lucky, you found it with the ultrasonic equipment. If you're unlucky, it's already went bang, because that mechanical damage is already significant. So we don't want to rely on the ultrasonic equipment anymore. We must move to the acoustic emissions with that higher frequency signal and that earliest possible leak detection. Has anybody got a guy in your maintenance team that says, I don't need any fancy equipment, I'll just use a screwdriver? And you got that guy? See this guy? He's dangerous. He's walking about the plant with a screwdriver. He's listening. Most of these guys are also quite, let's just say, experienced. In terms of age, the number is higher. They've already lost the capability to even listen to 20 kilohertz because they've been in and around mechanical components their hearing's a little bit less. That guy with the screwdriver telling you where your leak is living in cuckoo land. He's got no idea what's happening over here. And by the way, if he's poking rusty old valves with a screwdriver, don't stand beside him. Remember, human-induced failures, 40%. That goes bang. I was on a, it's a funny story, I was on a process plant in Scotland. I won't tell you who the operator was, but they closed the valve and the whole process pipework started shaking and rattling, and I'm getting really nervous here. And I said to the guy who I was standing beside, this is like an old operator guy who's seen everything, done everything. And I said, look, I'm a bit nervous about all this like vibration and everything that's going on in the plant. Should we not like move away from the area? He goes, no, everything's fine. But if you see the soles of my feet, run in the direction I'm running in. I'm like, you can't run fast enough to get away from an explosion. That's not going to happen. So don't rely on the guy with the screwdriver. I mentioned before, the easiest thing to imagine is the life cycle of a valve is going to follow the late life failure model in the bathtub curve. So late life failure looks like that. We've got this steady operating state. When the valve was brand new, just clarify for everybody in the room, every valve leaks. People talk about zero leakage. It's not happening. Every valve leaks. Every time you operate a valve, you put the seat to seal interface at risk. Even when the valve was brand new and it went through its factory acceptance test, there was an allowable leak rate for that manufacturing standard. And that's to make the valve cheap to sell. If you want every valve to be zero leakage, at the manufactured stage, you're going to have to pay a lot more for your valves. Nobody wants that. So the standards effectively say, ANSI, API, all the standards say there is an allowable leak rate for that valve when it's brand new. So even when you put that valve into service brand new, it's leaking. But it's leaking at a tolerable limit. You start operating that valve, any debris, any foreign particles can scratch the seat to seal interface, that rubbing action, whether it's a sliding gate or a rotating ball or whatever. Your seat to seal interface is at risk with every single operation. So the first time you operate the valve, you could have created a leak path. You don't know it's there because we don't have X-ray eyes. And we didn't previously have the tools to be able to find it. We now have the tools. The more times you operate the valve, the more that opportunity for foreign particles is going to create more leak paths. The longer you leave that leak path in play, the process fluid coming through that leak path is going to start doing that erosion exercise that I mentioned earlier on. So the erosion, the stripping away of particles makes the leak path bigger over time. And that's why in late life, you'll see exponential rate of change in your leak rate growth over time. Without condition monitoring equipment, you have no idea where your valve is on that life cycle today. And this could be tens of thousands of valves. Tens of thousands of valves. Typically 10 to 15% is what we find doing surveys need action. The other 80, 85%, 90%, you can leave them alone. So what this condition monitoring tool is going to do is it's going to do the survey, it's going to report back to you. Certainly we don't want to cross this line here, BER, beyond economic repair, but we're going to give you traffic lights. Green says that valve is okay, we can leave it alone, it's doing what it needs to do, it's got a tolerable leak rate. Amber says we're now between 50 and 75% of the allowable leak rate. We want to think about planning maintenance on that valve. We're not ready to do it yet, but at some point, if we've got a planned turnaround, we can put that valve on the list. Once it goes red, it needs to be on that turnaround planning list because you want to make that intervention. It's already exposing you to risk. Now you can play about with these numbers. You can change the percentages. We've got 50% and 75% as default settings. I've got a customer in Holland who said, we've not done maintenance for 7 years on our valves. If I went out and surveyed every valve, probably every valve would be red at 75%. So I'm changing amber to 100% and I'm changing red to 200% of the allowable leak rate so that I can still prioritize my repairs because I've not got the budget. I don't have the time scale to repair every single valve in the next turnaround. So manage risk, play with those equations yourself, and think about allowable leak rates. This is probably the hardest thing for customers to get their head around when you start having this discussion on the plant. People immediately go to ANSI, API, all those leak rates that you've been working on when the valve was brand new. Brand new allowable leak rates have got nothing at all to do with allowable or tolerable leak rates in your process. So again, one of those little resources that I said you can download from my LinkedIn page or from our website talks about what is an allowable leak rate. How do you define that? Where does it come from? And how do you manage that over time? And that's probably one of the most important parts of this discussion. The tolerable leak rate in your process is not the manufacturer's standard factory acceptance test allowable leak rate. Once you answer that question and get everybody on your plant to understand it, you'll have a much better understanding of how you can be deploying this technology. So we said, collect the data in the first instance, find out where your problem valves are. Don't let that flare emission happen over a long period of time. Go out, do those troubleshooting exercises and go to the root cause and fix that as soon as possible. Because the longer you leave that leak in play, the bigger the volume of total leakage in terms of emissions you're going to see on the plant. You're then going to want to move towards value-based exercises. Where is my biggest leaks? That's where I can get the best return on investment in the shortest time scale. And can I trend and report that over time? How is my leak rate changing? So the great thing about this technology is it takes about 2.5 minutes to do a survey on a valve. So remember that pressure build-up test I was talking about on your critical valves? So one of our customers said to us, it takes $3 million to do a pressure build-up test on one of our riser valves offshore. The EPA have mandated that we do that once every 30 days. If we don't do it within 45 days, we get fined. So effectively, every single riser valve in that customer's population is being tested every month at a cost of $3 million. So you multiply that over multiple riser valves on each platform, multiply that over multiple platforms, it's costing a hairy fortune. So we said, why are you doing pressure build-up test? We can give you the same certainty of leak rate quantification using this tool in about 10 to 15 minutes. So that $3 million you're losing in downtime can be returned to your profit. That's why we won the award for the Energy Industry Council. We moved the dial. A few $1,000s versus 3 million. It's a no-brainer exercise. So it's not about big data. Yeah, I've said already, people talk about big data. For me, the only data you're interested in is actionable evidence. What is this data telling me I need to do with my valve population? If we can get that answer from the system, and you can see in all our reporting structures here, all our filtration of data takes you to value-based maintenance. No more guesswork, no more confusion. You're only spending your maintenance budget on where it's required. So allowable leak rates. Again, I said this is probably the hardest bit to get your head around if you're just finding this technology today. So here is a survey that I personally did on a plant on 10 valves so that we could have this discussion today. Out of those 10 valves, which valve is the most interesting to you in terms of your maintenance investment? Which valve are you going to repair out of those 10 valves? What's your target valve? Number 6. Why have you chosen number 6? Why would you choose that valve? Yep, it's the most obvious answer. The leak rate is higher than the rest. Now, if all these valves are on exactly the same process line, with exactly the same process fluid, with exactly the same risk profiles, clearly valve number 6 is the target valve. Biggest risk, biggest loss of efficiency, could be biggest lost product. However, here comes the caveat. If these valves are not all in the same process, the biggest risk might actually be valve number 4. That 0.1 litres of minute of leakage is benzene going into an area of the plant where there are humans walking about. What's your biggest risk now? So we have to understand what's the process fluid, what's the risk profile, and then we can start to do our analytics to focus our attention where it's absolutely necessary. This is not just a leak rate equation. So that exercise I said, where we exported to the CSV file, went to the column, that prioritization gives you leak rates, yes, as we would want to look at leak rates, but the next layer of value has to come from understanding the process fluids and the risk profile attached to each of those valves. So again, what I'm trying to say here is we have to have a serious conversation about what an allowable leak rate is, and you have to be able to answer the question why you've selected that profile for that valve. We always get asked, what is the smallest leak rate you can find? Well, the answer is actually on the screen. On a big valve at low differential pressure, we're not going to report anything less than 0.1 litres per minute. In terms of the bigger valves, you know, I spoke to Rajan about what sort of leaks are you trying to find on the process plant. So this is Chevron. And he said, I would like to find 0.1% of the flow rate in terms of a leakage. Okay, so that's about 1,000th of the seat to seal interface would be a leak path. He said, I would be happy if we could quantify a leak rate that's somewhere between 1 and 2%. If we could do it between 1 and 2%, we would probably invest and roll this out across the whole of Chevron. So if you can prove that works over that scale, this is literally a current conversation we're having. If you can prove it works on that scale, we can go on a rollout program. And I said, I'm more interested in the 0.1% because I'm sure we can do the 0.1%. And this is what it's all about. It's not about going to that smallest leak rate you can find. Yes, we want that earliest possible indication, but we have to understand risk. The key part of the discussion is risk. So don't just be confused by finding the smallest leak. Find the important leaks at the earliest opportunity is my advice. And consider what is a tolerable leak rate in each of your valves within the process. So allowable leak rates are not factory acceptance test standards. It's not the smallest leak you can find, and it's not what's defined in the as new valve factory acceptance test standard. It is what the process can tolerate, where the risks are in your process. Is it a human factor? Is it an environmental factor? Is it a process efficiency factor? How do we manage all those risks? And the answer is very simple. We go to a risk-based inspection calculator. What's the probability of failure? What's the consequences of failure? All we ask you to do is go to that drop-down box and click low, medium, high, or none. It's as simple as that. That's going to guide you which valve to survey when. Because again, that's one of the frequently asked questions. How frequently do I need to survey that valve to manage that risk? As a minimum, you want to be doing surveys on the same time periods as what you used to do your maintenance interventions. Ideally, you want to have better resolution on your data set than that. But as a start point, you could start there. I'm not sure how long it is since we did it, the Wynnewood refinery. It'll be a few years now. We might want to go back and look at all those same valves again and compare the data set and say, okay, how's that trending? Has that valve that had 0.1 litre of leakage per minute now gone to 0.2, or are we at 0.5? Yeah? Or have we completely run off the scale and we're getting several litres per minute going through that valve, increasing our risk profile? So again, it's this concept of manage the risk over time. We've got a couple of YouTube videos up. We've got a YouTube channel. This is us doing a time-lapse survey on a valve. This is in a flow loop, so it's a 4-inch ball valve, I think. And what we wanted to do was show you just how quick and easy this is to use. So that pressure build-up test technique that I told you, on a valve like this, it could take 2, maybe 12 hours to set that up. So if your process plant is operating with $1 million revenue per day of process output, and you take 12 hours to do that test, you've now lost $500,000 just doing a test. So in this little video on YouTube, we show you that survey doesn't need to take 2 to 12 hours. That survey took 2.5 minutes. And our little handset calculator device showed an immediate result while you're still standing next to the valve. You know whether you need to do immediate intervention, maintenance, or put it on a planned schedule. We also have another little video clip where this ugly bald guy talks you through. It takes about 12 minutes. So this is the demonstration that I'll give you if you come to our exhibition stand and you play with the manifold. I'll let you go hands-on with it. You can go on the valve. We will also have our permanently installed sensor, so you can see how that might be put into play in an automated fashion. Within your control room, you can see all the valves on your flare line, and you don't have to send the guy out to do a 100 valve survey. You can just sit in your control room and go, that valve's gone red. Go into more details. I can see the leak rate. I can also estimate the cost that is now losing in process fluid. So anybody that needs a bit of convincing about making that maintenance intervention, when they see that lost number, immediately goes, get somebody out to fix that valve. Okay, we'll show you all these things on the stand. Won't run that just now. There's a training course that comes with this. So whilst I've said I can train you to use this in 30 seconds for leak detection, what you really want to do is move to that second and third layer of operation, where you're doing leak rate quantification and leak rate trending over time. In order to do that, you need to understand the software. So what we do on the training course is we talk through scenarios. We talk through anything that can undermine the quality of your survey, those potential banana skins, and there are a few things like bypass valves, things that customers just don't really think about in advance. We run through all that. We then talk about the software, how to get all the data in, how to extract the value out, how to produce all the reports. And then on day 2, we take your guys out on the plant and we get them to do surveys, and we supervise that survey work so that you can be self-sufficient from day 3 onwards. I am no longer on the plant at day 3. It's a 2-day training course. So we've got lots of case studies. Again, as I said before, we will have that QR code that I'll share with you. You can scan that. There are about 15 ways in which this tool contributes to what we describe as our emissions elimination program. So using that multiple tool set, you can go and access those 15 surveys and see how we've added value in each of those examples, whether it's an environmental impact, a sustainability impact, a reliability or a process efficiency impact. These are all positive outcomes. What we want to do is have something in your hand that gives you the correct focus. I showed this next slide to the EPA at the Valve World Conference. Again, I'm probably going back 8 years, and everyone was talking about parts per million of leakage. So as you go around all these conference presentations, you'll hear everybody talking about parts per million. What's the allowable stem leak on this valve? And it started off at 500 ppm, then they reduced it to 200 ppm, and we're aiming for 100 in the near future. But really, the target is to go to 50 ppm, and we've got this low E emissions pack-in and all this stuff. And guys, you're missing the point here. Is there nobody from the EPA in the room? And this poor woman stuck her hand up in the room and said, yeah, I'm from the EPA. I said, I want to show you a slide. This is a slide. When you chase parts per million of leakage of valves, you're effectively the fire department coming round to put out the wastebasket fire while the city burns down behind you. And the reason for that is that these highly sensitive tools that can find the ppms of leakage in your valves, in your flange joints, are cumulatively finding something like a couple of tons of leakage per annum. Do you have the maintenance resources available to make that go away? If you do, you're going to have a massive budget, making the difference of about a couple of tons. If you've got flare line valves that are leaking and you can't find the leak, those tons of gas are going up into the atmosphere potentially on a daily basis. What do you really want to spend your money on in your maintenance budget? If you want to make an impact on environmental performance, sustainability, and reduce flaring and venting exercises, you need to go after the big leaks. We don't want to spend all our time rummaging about in the waste baskets. We want to keep the city safe. So let's go after the tons. And again, you'll see on our demo, open our valve slightly to simulate a leak. You've got tons of gas going up that flare stack. The more days that that valve sits in the non-performing condition, and it could be something as simple as a relief valve. The relief valve, a little bit of debris goes between the seat to seal interface. The disc can't go right back directly onto the seat. That's now sitting open all the time. Tons of gas going to flare. So I'll give you an example of a survey we did in England. We were asked to survey 460 valves using MIDAS meter, quantify leak rates. And at the end of the survey, we said, if you fix 2 valves in your population of 460, you will reduce your total emissions on this site by 66%. There's about 80 valves leaking. Repair 2 of them, and you'll reduce your emissions by 66%. Imagine the power of being able to do that. Go to your maintenance guy, go to your CEO and say, look, we've reduced our emissions. All those guys sitting trying to earn their bonus in the C-suite. And by the way, maybe your bonus is tied to it as well. I always said to people when we started selling this device, this is not a brand new device. We've been selling this for about 12 years. I always said to the guys, when you use this device, this is what I want you to do. Do the survey, sort the data, and then go into your boss's office like, hello, I've got the MIDAS meter results here. We're going to fix this small number of valves to give you this outcome. And when your boss gets really excited and starts smiling, the next question is, can I have a pay rise? Because that's what we're going to make go away. All that extra cash that you're going to be making in the process, all these extra millions of dollars you're getting back, you can afford to pay me a pay rise. I'm just having a bit of fun there, but in the big scheme of things. Pay raise, yeah. If you've improved the efficiency and you're the maintenance guy, that's great news for you. Look how effective I've been. Our emissions on scope 1 operations went from 50 tons to 2 tons. By the way, we never fixed any fugitives. We only went after the through seat leakage. That's great news. So we have to think about the value of data and where we're really adding value. Some of that message, I think, is starting to get through to the EPA, and they're looking at other ways to monitor and measure. The whole ESG, environmental social governance issue, sustainability and reliability over time, is driving this further and further in our direction. If you don't know the data, you can't take the right action. So it's not about big data, it's about understanding where the data comes from. We do have 2 presentations in the conference, one of which I'm going to tell a story about something that happened quite close to here, where we surveyed a whole population of valves, 62 valves. Out of that population of 62, there was 8 leaking, and we were able to save the customer $342,000 on their maintenance program. That's before we even start talking about product losses. And by the way, they also wanted to install a $2.5 million air scrubber to strip the gas back out the system, which they no longer needed to do because they just addressed the leaking valves. You don't have to filter out gas if the gas doesn't exist in the first place. So it's about root cause analysis. So understanding all these models, understanding all these case studies, as I say, we'll be running through this in the presentation. Coming back to our reliable leak rates, what are the insights that we are delivering back? If we're taking this valve survey here, again, these are real survey data that I've just mentioned from that local survey we did here. These are the 8 leaking valves. Which ones are we going to fix? So on the left-hand side, we're looking at annual losses financially. So the CEO is looking at this and saying, guys, get after valve 4, then number 5, then number 3, then number 7. But if you're looking at it from an environmental perspective, on the right-hand side, pounds per hour of lost product to flare, we're chasing valve number 7 first, and then we're going to number 4, and then number 5. And we're in the law of diminishing returns. So think about how you're slicing and dicing data. Where are the insights? Where are we adding value? Financial focus, valve 4, environmental focus, valve 7. Data we have, the better the insights we get. So I mentioned our other potential failure modes and other systems are in play, other sensors are in play to try and find those other failure modes. It's not just about the fugitive emissions. We can have valves that are stuck in a partially open or fully open position that are causing much more damage than anything that could be coming out the stem packing. So let's understand that, go beyond just the leakage data, and yes, quantify it, yes, go on our traffic lights, yes, pursue the red traffic lights, report it in this fashion here. All our leakage rates against our allowable leak rates, and there's all our traffic lights guiding us where to make our maintenance intervention, where to spend our maintenance budget. Actionable insights, leak rate change over time. Sometimes we see spiky graphs like this one. So if anyone's done maintenance on this valve, you might see what started off as a red traffic light turning back to amber or even green. That might be as a result of temporary repairs, or it could be someone fitting an OEM spares kit. In this instance here, the reason I've used this graph is because what we can see is we went from a red traffic light back to an amber and all the way through to a green. Now, if you stopped there and there was nothing in the graph beyond that, you would imagine either the valve's been replaced or the valve has been fully stripped down and OEM parts installed. But if you look at the next survey result, we're already back at a red traffic light. So for me, what's happened here is a temporary repair. That could have been just exercising the valve. And the green could have been sealant injection. Problem with sealant injection, of course, is the next time you operate the valve, the sealant gets flushed away and you're back in a potentially worse position than you even started in. So important to understand all these data insights, where we sit on this graph at any one point in time. This is not a perfect science. No measuring tool will ever give you perfect science. So again, we run through limitations, we run through examples of where there could be challenges. On the training course, we talk about things like insulation. So we have these little waveguide devices that we can attach to the front end of the sensor, which allows us to access more valves, whether it's in a thermal challenging position outside the safe operating temperature of the sensor, for example, cryogenic valves, steam valves. We use this as a thermal protection, but we can also use it as a mechanical reach to go through insulation. So you don't have to strip out all the insulation. You can just create an inspection point to get you back down to the metal substrate. So we mentioned once you get into the most critical valves, you want to have the permanently installed sensor doing continuous monitoring. That is the permanently installed sensor. Exactly the same devices in the front end of here, doing the same work, but you've left it out on the plant in real time, all the time. It's now talking back to the control room. So if there is 100 or 500 valves on the flare line, you're now looking at a graphic user interface that says all the valves are good, everything's green, I'm not worried about any of these. If anything goes wrong, suddenly you can now see one of the valves has turned red. I can drill into more valve details. It'll tell me the acoustic readings, it'll tell me what the leak rate going through the valve is in whatever units you select, and it can even calculate the cost of that leak, which in this case, because we've entered a unit cost for process fluid, is about $3,500, and I put that in British pounds, GB pounds, that's about $5,000 per day going through that valve. And it's not a big leak. 6.5 litres per minute. People imagine 6.5 litres per minute is a big leak. I'll put this in perspective for you. If you just hold out your finger and blow gently on it like that, almost like you're whistling, that's about 5 litres per minute of leak. It's literally a whisper leak. So think about that on gases as well. These are not big numbers in terms of leak rates, but they're big numbers when you start calculating the cost of the process fluid that you're losing. In the most complex systems, this is a graphic user interface for our VMAP system. Again, we're talking about 48 different failure modes being monitored here. This is a system that is installed in Norway. Since we made that graphic, they've extended this by another 50%. So there are actually 62 valves now being monitored with our VMAP system, trying to get to the root cause on those 48 failure modes. I should point out that we cannot predict electrical failure. So we're actually only able to predict 47 of the potential 48 most common. But I think we're doing okay there. That's 95% diagnostic coverage. A lot of discussion in the marketplace about wireless systems. If you want these permanently installed kits to be wirelessly transmitting information back to the control room, we can do all that already. It's not a limitation of this technology. So we were all about 3C leak detection, quantification and trending. We said we did that with our handheld device and our permanently installed device. If we want to go to the other failure modes and effects, we have to start deploying other tools. So we do have some of these other tools with us this week. We'll show you some of them upstairs, or rather hotel. I keep saying upstairs, it's not here, it's at the Hilton. But we'll show you these other technologies. This all contributes data into our intelligence cloud that allows us to optimally manage large valve populations on behalf of our customers. And that's effectively what we are. We're a valve management company. And maintenance routines can be challenged because not all are adding value. What we want to do is use the data to drive our behaviours to the most efficient and optimized model of valve management that we can possibly implement at any one point in time. This will change the way you have been operating in the past and make you much more efficient and effective moving forward. All of this gives you a massive return on investment. Regardless of who you are on the process plant, there is value. So I mentioned this earlier on, most operating companies, when you go and speak to certain individuals on the plant, they'll say, what's in it for me? You know, why should I bother? What value are you going to add to me? So I put this matrix together just to show this is not just about the maintenance team. It's not just about the environmental team. This goes from everybody on the plant all the way up to the C-suite. Everybody can extract value, whether it's just finding the poorly performing valves through to trend and degradation and performance over time. Everyone is going to get a return on investment in interacting with this technology. Case studies all focused on financial elements, sustainability elements, management of risk in the broadest possible terminology. As I say, this is not brand new technology. We've got lots of happy customers around the world. Pretty much every blue chip company that you would expect to be playing with this device has played with it somewhere in the world. So if you're sitting there in a company that's not used it already, we can probably put you in touch with someone in your organization who's at least had an on-site demonstration or deployed it for troubleshooting or gone all the way right through to risk-based inspection deployment. Testimonials from those people. Training course generally gets excellent feedback because we're not just telling you about what the tool is and what it does, we're showing you where it adds value. So in terms of coming to a conclusion, what we can say is that this is, in obviously our opinion, the best available technology to take you to that new operating level where you're not going to get the same old return on investment that you got. We're moving to a new position by doing things differently, disrupting your old methods of working to take you to value-based maintenance, but you will only get the benefits when you start deploying the technology. So key message, let's not wait any longer to get it deployed. let's not wait any longer to get the insights that are going to drive us towards new behaviours and optimised performance. That's really what I wanted to share with you today. The links to our online equipment descriptions and case studies are all on the screen there: YouTube, Twitter, LinkedIn, our landing page, our website. If you do want to scan the QR code just now, I'll bring that out and put it on the tables for you, and we can start sharing even more information that helps you on your journey to where we want to get to, and that is 100% reliability in 100% of your valves 100% of the time. Thank you for your attention. I hope you got some value out of that today. We will be on the stand up in the Hilton Hotel showing you this equipment and a few other bits and pieces, so please drop by our stand in the main hall. If you can come to any of my other 2 conference papers as well, I'd be delighted to see you there, and we'll talk about some other value that we've been added for other customers. Is there any questions that anyone has right now that I might try and answer for you?
So, as noticing if we put the permanent installations in, and then we tie them back to central, how you described it, but I would see in that case probably central not necessarily being our process control room, but some other, like a maintenance shop, you know,
Sure.
or my office. I don't know. But do y'all set up that software and everything, and you saw a little display there that it would,
yeah,
you would tie it into that, and it could either be hardwired or
wireless.
Wireless,
yeah. So, I mean, different customers play with these technologies in different ways. Some customers like us to do the reporting and infrastructure, monthly analysis, so we can set up all that support infrastructure in and around even just what the sensors are telling you. But if you want to be completely self-sufficient, we can install that. You can take complete control of it. If you want us to come and do the access, then there's security protocols, firewalls need to be in place so that you're protected, we're protected, and you know, the IT team gets involved at that stage. It's not just the sensor guys, but we'll install all the sensors, we'll wire it back, or we'll wireless it back to wherever you think you're going to get the best value. As you've rightly pointed out, that could be in the maintenance team, could be in the central control room, could be anywhere. It could be your head office and wherever that is. Running a little calculator device on all these leak rates really starts to focus attention pretty fast, because it's money that you effectively don't need to lose. And the system will pay for itself literally the first time you have a properly organised planned shutdown. You get more back than what you're ever likely to spend on installing the system. That plant I showed you in Nyhamna in North Norway with the 62 valves on our VMAP system, that was installed in 2004, and the total number of unplanned shutdowns they've had since 2004, which is 19 years, the total number of unplanned shutdowns they've had, 0. 100% reliability over 19 years. That is awesome. So that's what we want for all our customers.
And I noticed too on the remote or the remote automated ones, the continuous analysis is just a single monitor on a valve. But when we do it with the hand, we take multiple. Is that?
Yeah. So what that didn't really show you too well, because it was just for graphic representation purposes. When we installed the sensors on site, I have to watch what I'm saying here, because there are other manufacturers who take different approaches. The only way this system works is if you know what the process noise is. Otherwise, you're going to get incorrect answers. So what we do is we install sensors upstream and downstream of the valve, as well as on the valve body. That's the only way you can get the right answer. Anybody who tells you any different doesn't understand the technology and doesn't understand the limitations. So that's a clear message.
And then if you're in a process someplace, the distillation tower, and you're, today you're running at 10% of your stream is C4, and tomorrow's 50% is C4. How does that affect you?
So the key things that you saw on that graphic user interface, yes, you saw the financial, yes, you saw the calculated leak rate, yes, you saw the allowable leak rate. The other two pieces of information is what drives those calculations. So that the algorithm needs to know all the valve parameters. So that's already pre-programmed, it's in the background, it's ready to do the calculation. The two core pieces of raw data that get you to the calculated leak rate number is acoustic reading and differential pressure. So we also need to tap into pressure sensors that are in your system. If they're not in your system, we need to install them in your system. But that can be done at the same time as installing the sensors. So again, that's something we would have a discussion with you. Do they already exist? Are they automated? Can we access that data? It may be plug and play already from your existing infrastructure. So again, IT guys will fix all that in terms of the configuration element to it, but we would need to know what the pressure is at any one point in time to give you an accurate leak rate calculation. So two ways of looking at leakage. We can do it by mass or by volumetric. If we want to do it by mass flow, we need to know the density of the fluid. What I normally say to people is when we start with this device here, rather than doing all the backstory of looking at every single process and working out what density is at every point in the process, the easiest thing to do is just start on volumetric flow.
But you don't need the specific gravity to do volumetric.
Yeah.
Just
So when we did your survey, you'll see that all the results are listed in volumetric flow. Excellent. Well, if there are no more questions, I'll thank you for your attendance this morning. I don't think you signed the attendance sheet, so I'll give you one of my cards. You could pop your name on the list here. Just for the organisers. Thank you.